If you think gravity, just that cute little coincidence, the universe tossed in, so things don't fly apart in every direction, then hold on, because what I'm about to tell you is going to make that idea seem adorably naive. And I say this with all the affection of someone who spent a lifetime peering into the corners nature deliberately tried to hide. You know, we tend to think physical laws are cryptic spells written in weird symbols, but really they're just the universe's whispers. Whispers that for some reason it's agreed to let us overhear. And when you listen long enough, you start to realize those whispers are never messy, never moody, never whimsical, the way humans are. They're precise, stable, and reliable, to the point that if you change one tiny detail, the entire universe would fall apart like a clock, missing a single gear. That's the nature of physical laws. They don't just describe how the universe works. They are how the universe works. And the fascinating thing is, we didn't invent them. We just stumbled upon their traces, as if nature occasionally forgot to hide a few clues. Physical laws have to pass the strictest test you can imagine. They must hold true everywhere, not just on Earth, not just in the lab, but in the darkest corner of a galaxy, millions of light years away. If a law only works inside your house, it's not a law. It's a personal preference. And what always delights me is that humans with our watery eyes and walnut-sized brains can peer so deeply into the universe that we catch the patterns it lets slip, not because we're so smart, but because nature is kind enough to give us a chance. You see, if planets moved randomly like kids playing with water guns, Newton would never have noticed anything. If the moon zigzagged whimsically, you could toss all the math in the trash. It's the repetition, the regularity, the sheer stubbornness of the universe, that orbits have to be orbits, that forces have to be forces, that lets us see the laws. That's not coincidence. That's an invitation. And of all the invitations nature has sent to humanity, gravity is the most formal. It's simple enough for a child to grasp, yet profound enough that we're all still fumbling to understand it more. It's beautiful in the way a perfect curve has no excess, no shortage, no flashy sparkle, just right, absolutely right. And when something is absolutely right from dust mote to galaxy, it simply cannot be random. You can't roll dice and hope to get an equation. You certainly can't roll dice and hope to get a universe that runs precisely according to that equation for billions of years. When I say gravity cannot be a coincidence, I'm not talking philosophy. I'm talking mathematics, physics, and observations that repeat like a flawless classical score that never misses a note. And so before we dive into the more exciting part, how people like Bragg, Kepler, Galileo, and Newton peeled back layer after layer of this secret, I want you to do one simple thing. Temporarily forget what you think you know about gravity and look at it as if for the first time. See it as a sign, a signature, or even a trace of a deeper order the universe is running on. And if you're willing, if you'll sit in this chair just a little longer, I'll show you what I've spent my life chasing, that gravity is not just a force, it's a story nature wrote in equations, and we're lucky enough to read. So shall we begin? Look straight at what Newton saw. Between every pair of objects in the universe, no matter how big or small, heavy or light, there is always an attractive force, and that force can be described by an equation so short it's almost unbelievable, like a quick note scribbled in a notebook. F equals sign J, frac m underscore 1, m underscore 2a eta Deborah, squared Deborah. The entire phenomenon of gravity packed into just one line. Two objects attract each other in direct proportion to their masses and in inverse proportion to the square of the distance between them. Not the distance, the square of the distance. a mathematical choice so precise that even a tiny deviation would mean the universe as we know it couldn't exist. And what fascinates me most is how intuitive it feels. The farther apart two objects are, the force weakens very quickly. Double the distance, the force drops to 1/4. Triple it, 1/9. A rule so simple a child can understand it, yet subtle enough to force planets to follow perfect paths for billions of years. Take the moon as an example. It doesn't wander across the sky like a cosmic sleepwalker. It is falling steadily, gracefully, and precisely. Every second, it falls exactly the amount the equation predicts. If gravity were even slightly stronger or weaker, the moon would either crash into Earth or escape into the deep void. A motion so beautiful cannot be the product of chance. You can't roll dice and expect them to produce a concise equation that exactly describes the motion of every celestial body, from the solar system to distant star clusters. Let's go back to the late 16th century, when the night sky was still a mysterious curtain and humans had no telescopes, no computers, no concept of equations describing the universe. All that existed then were eyes, a few wooden and metal instruments, and the absurd ambition of one man history would later call an eccentric genius, Tycho Brahe. When Tycho died, Kepler fought hard for access to the data, but once he got it, the astronomical revolution began. From 1601 to 1609, Kepler dove into analyzing Mars data, the most stubborn planet with the most deviant orbit. He tried every model he could imagine: Ptolemy's circles, spirals, epicycles, polygon, the music of the spheres, but none matched Tycho's ruthless precision, a mere 2 arc-minute discrepancy, and Kepler discarded the model instantly. Finally, he had to confront what he himself had once resisted: planetary orbits aren't circles, they're ellipses. In 1609, Kepler published Astronomia Nova, and the first law was born: planets move on elliptical orbits, with the sun at one focus. This shook European astronomy, because for 1,500 years, the circle had been seen as the perfect shape the universe must use. But Kepler didn't stop. He realized planets move faster when closer to the sun and slower when farther away. This wasn't planetary caprice. It swept out equal areas in equal times, a beautiful but precise mechanism that made Kepler shiver. That was the second law. It doesn't just describe motion. It reveals a rhythm, a heartbeat of the universe. When Kepler wrote that he felt he was hearing the music of the spheres, he wasn't joking. Orbits, speeds, and distances harmonized like notes in a symphony. In 1619, after 18 years wrestling with the data, Kepler finished the final movement, the third law. The square of the orbital period is proportional to the cube of the semi-major axis of the ellipse. This law tied everything into a system. Know a planet's distance from the sun, and you can calculate its period. No guessing, no gods, just mathematics. And this is when the universe revealed the most important thing. No randomness could produce 3 laws so beautiful and precise. The sky isn't whimsical. Gravity isn't random. Planets don't improvise, speeding up and slowing down. Everything obeys a deeper order. Kepler touched but couldn't yet express in complete mathematical language. Kepler had the data and intuition, but not the tool. He saw the music, but not the conductor. And then, about 60 years later, a young man named Isaac Newton would read Kepler's 3 laws and say, "I know who the conductor is." Newton would turn all that beauty into equations, logic, a system. He would prove that what Kepler found wasn't just patterns in data, but the signature of a fundamental force of the universe, gravity. But to grasp how great Newton was, you have to see that the entire journey began with Tycho's eyes and Kepler's obsession. Two men who never knew they were laying the foundation for proving a far greater truth. Gravity cannot be a coincidence. It's too precise, too consistent, too beautiful to be mere luck. While Kepler was decoding planetary motion in the sky, elsewhere in Italy, another man was observing a much closer form of motion, the fall of objects right before our eyes. That man was Galileo Galilei, and his discovery about falling bodies would open the direct path to Newton and the law of universal gravitation. For nearly 2,000 years before Galileo, Aristotle's philosophy ruled. Heavier objects fall faster because of their nature. It sounded reasonable, and more importantly, no one really checked. But Galileo was different. He didn't care what sounded right. He cared what was actually right. And the only way to know was to experiment. Around 1589, 1592, records show Galileo dropped two spheres, one heavy and one light, from the Leaning Tower of Pisa. Though this famous experiment is debated, what's certain is that Galileo conducted precise experiments with inclined planes, timed falls with water clocks, and reached a conclusion that shook ancient philosophy. All objects fall with the same acceleration, regardless of mass. This wasn't some cute coincidence of nature. If gravity arbitrarily pulled heavier things harder and lighter ones weaker, or changed mood day to day, Galileo's experiments would never have given consistent results. Science wouldn't exist. But Galileo observed hundreds of times, and every time free fall acceleration is constant. Gravity doesn't discriminate. An incredibly profound idea, and this doesn't just hold on Earth. In 1971, astronaut David Scott on Apollo 15 repeated Galileo's experiment on the moon. He dropped a feather and a hammer at the same time. In the airless environment, both hit the ground simultaneously. Two completely different objects, same motion. This is the most perfect proof of what Galileo discovered over 350 years earlier. Gravity treats everything the same way. Pause and think about this. If gravity were coincidence, it couldn't repeat so exactly on Earth, on the moon, in the lab, in space, and across hundreds of years of measurement. No luck lasts that long. This very consistency is what made Galileo great. He was the first to show that nature can be described by laws, not vague explanations. And from there, a bold idea emerged. If everything falls the same on Earth, could the moon be falling under the same rule? That sounded insane at the time. But it was exactly the bridge between Galileo and Newton. Galileo proved that falling acceleration is independent of mass. Newton later realized this meant the attractive force on an object must be proportional to its mass, a key to building the gravity equation. If Galileo hadn't shattered Aristotelian thought, if he hadn't proven by experiment that motion follows consistent laws, if he hadn't dared question 2,000 years of history, Newton couldn't have asked, if the apple falls, isn't the moon falling too? And without that question, there would be no law of universal gravitation. Hidden in Galileo's discovery is something far deeper. The universe isn't arbitrary. When you drop an object, gravity pulls it down the same way. Today, tomorrow, next year, in Italy, in America, on the moon, as if the universe keeps giving the same answer to the same question. It's that repetition that allows science to exist, and Galileo was the first to hear it. So when you see two objects fall together, don't think it's obvious. It's evidence that gravity cannot be a game of chance. It's consistent across everything. And that consistency is the foundation stone Newton stepped onto in history. When Galileo showed the world that everything falls the same, he handed humanity a key no one knew how to use yet. It took Newton to turn that key and open the door to an equation describing the entire universe. And the most astonishing thing is that the moment Newton saw the unity between a falling apple on the ground and the moon hanging in the sky probably happened when he was barely in his 20s, living during England's plague lockdown. The apple falling on his head story is often retold as a funny anecdote. But the important part isn't the apple. It's the question Newton dared to ask. If the apple falls because Earth pulls it down, isn't the moon falling in the same way? This wasn't a poet's question. It was the question of a mind that saw unity where others saw two unrelated phenomena. A small object falling straight to the ground, and a gigantic celestial body moving forever without touching down. Newton understood that the moon doesn't fall down only because it's always falling sideways, and that sideways fall perfectly matches orbiting Earth. What he needed now was the rule for the force that makes the apple fall and keeps the moon in orbit, and that rule had to hold for every object in the entire universe. Now Newton turned back to the numbers Kepler left behind and asked what force could produce exactly elliptical orbits, exactly equal areas swept, exactly the orbital periods Kepler described. Not just any force would do. Newton tested different forms: inverse to distance, inverse square, inverse cube. And only one form made the math snap together like perfect gears. Force inversely proportional to the square of distance. The inverse square law. This is one of the most beautiful discoveries in the history of science, because the inverse square law can arise from extremely simple intuition. Imagine a source spreading influence in all directions. That influence spreads evenly over the surface of a sphere. Sphere surface area grows with r grad, so influence must decrease as 1 r grad. That's it. No poetry, no philosophy, just basic geometry. But that creates the universe. Newton applied this rule to Kepler's data when he set the force between Sun and planet inversely proportional to the square of distance. He immediately saw that elliptical motion wasn't just empirical description. It was the inevitable consequence of the equation. Equal areas in equal times became a consequence of the force always pointing to the Sun, and the relationship between orbital period and distance emerged naturally from the equation. One single formula explained all three of Kepler's laws. This wasn't coincidence. This was a terrifying fit. But Newton didn't stop at planetary data. He wanted to see if the inverse square law could explain a falling apple. He calculated the curvature of the moon's orbit and compared it to the acceleration of objects near Earth's surface, and found that accounting for the moon's distance to Earth's center, the moon's falling acceleration is about 3,600 times smaller than an apple's, and the moon's distance from Earth is roughly 60 times Earth's radius. 60 cows equals sine 3,600. Again the square. Again the square. The way these two numbers matched so exactly couldn't be luck. It was like the universe planted a giant sign in the middle of the road. Here's your inverse square law. Newton saw it and understood instantly. But what fascinates me most isn't that Newton found the gravity equation. The most beautiful part is that he proved only this equation allows the universe to be stable. Imagine if gravity fell off as 1 Funt's error squared. Instead of 1 Funt's error squared, the force would weaken too fast. Planets couldn't hold orbits. The slightest perturbation, and they'd fly into dark space. No solar system, no stable orbits, no seasons, no life. Conversely, if gravity fell off as 1 Funt's error squared, the force would weaken too slowly. Planets would be sucked into the Sun like stones down a well. No beautiful orbits, no delicate balance between pull and sideways motion, no life. If the exponent, just that tiny number in the equation, changed by even 0.0, 1%, comma, the entire universe you're living in couldn't exist. Not hard to exist. impossible to exist. What does this mean? It means gravity isn't just a force pulling things to the ground. It's a strangely fine-tuned condition, a mathematical structure so beautiful, it's absurd, so precise, that if someone claims it's random, you have to ask back, random in what way that it's accurate to 15 decimal places? Newton couldn't answer what gravity is. He himself said he framed no hypotheses about its nature, but he answered the more important question, how gravity works and why the apples fall and the moon's motion are the same thing. He unified heaven and earth. No one before him had done it. It took 250 years after him for anyone to surpass him, Einstein. And the most important point here, returning to our theme, is this: all the evidence points one way. The inverse square law cannot be coincidence. It is the structure of the universe. It is how nature decided to distribute force. And it is the sole reason planets can exist, because only this form of force allows stable orbits, steady periods, and the emergence of life. Not luck, not chaos, not randomness, but order. An order deeper than anything Galileo or Kepler ever saw. And it was from that order that Newton wrote the equation we now dare call one of the most beautiful poems humanity has ever decoded from the universe. But what's even more interesting is this: even though Newton dominated science for 300 years, there was always one small detail he couldn't explain, and that very detail would pave the way for Einstein to rewrite the definition of gravity once again. Newton proved that only the inverse square law could produce stable orbits. But to truly see how precise gravity is, we have to look at the largest and most beautiful natural experiment, the motion of the moon. If there's any place in the universe where gravity might have a chance to miss a beat, it would be at a distance of more than 384,000 kilometers from Earth, where a sphere weighing 7.35 cots 10 squared kg hangs suspended, pulled downward by gravity, yet never touching the ground. And the moment Newton asked, how much is the moon falling, was the moment gravity revealed its terrifying precision. Imagine this: if you drop an object from a height, it falls because gravity pulls it down. The moon is also being pulled down by gravity, but instead of falling straight in, it falls sideways fast enough to miss Earth every time it falls. And that is exactly an orbit. When Newton calculated it, he found a bizarre result. The moon falls about 1/20th of an inch per second. Yes, in every second, the moon drops toward Earth by about 2 mm. But because it moves sideways about 1 kilometer in the same time, Earth curves away beneath it, just enough to create a perfect 27.3-day cycle. 1/20th inch per second is not a rough number. It is precise to the point that if you changed it by just 0.01%, the orbit would completely lose stability. Consider what happens if gravity slips even a little. If the moon fell 1/20.002 inches per second, the slight increase in acceleration would cause the orbit to gradually shrink, leading to a catastrophic collision with Earth in a few million years. If it fell 1/20.998 inches per second, it would float just a bit too much, and over time it would drift gradually outward, escaping the Earth system. Just 1 part in 10,000 of the falling rate, a difference smaller than the thickness of a hair across the Golden Gate Bridge, is enough to destroy the entire orbit. If gravity were random, or makeshift, or acute coincidence of the universe, then keeping the moon within such an absurdly narrow margin for more than 4.5 billion years would be completely impossible. But it's not just the moon's fall rate that is precise. Its entire motion is a mathematical symphony that never misses a beat. Look at the parameters. The moon's orbital eccentricity is 0.0549, just enough to create distance variations that give Earth's tides their regular rhythm. The orbital period is 27.32161 days, not 27.3, 2 comma, not 27.3, 3 comma, but accurate to 6 decimal places. The orbital inclination is 5.145 degrees, a number that determines we don't have solar and lunar eclipses every month. Shift it by just 1 degree, and Earth would be plunged into weekly eclipses. Those numbers could not exist if gravity didn't keep time with mechanical precision. And here is what is truly astonishing. The moon is constantly influenced by the rest of the solar system. The sun's pull is twice as strong as Earth's. Then there's Jupiter, small perturbations from Earth's elliptical orbit, tidal energy loss. Yet despite hundreds of perturbing influences, the moon's overall orbit remains terrifyingly stable, as though a natural correction mechanism always brings it back to the inverse square law track. If gravity were nature's randomness, it could not maintain such fragile balance. Remember, the moon's position has been measured by NASA, firing lasers at retroreflectors placed on its surface by Apollo astronauts. The result? Accuracy down to millimeters, meaning we can know exactly where the moon is in vast space with an error smaller than a screw. And after decades of measurements, one thing is always true. The moon falls exactly as Newton predicted. No deviation, no fatigue, no anomalies. It falls precisely to the millisecond, the millimeter, the thousandth of the acceleration the inverse square law demands. Something random cannot sustain that behavior through billions of orbits. Something accidental cannot reproduce itself with that accuracy over a time scale longer than the entire history of life on Earth. This leads to the unavoidable conclusion: gravity is not just strong or weak. Gravity is precise to a terrifying degree. Gravity knows exactly how much is enough. Enough to keep the moon in orbit, enough to create tides, enough to stabilize Earth's axis, enough to sustain the life you are enjoying. If gravity were 1% stronger, Earth would lose the moon. If 1% weaker, Earth would never have had it. Either way means no stable climate, no seasons, no biological cycles, no complex life. The moon is a perfect reminder. The universe does not play games of chance. It calculates. It is precise. It unifies from apple to celestial body. Every orbit of the moon is a clear signature of gravity, a force that never slacks off, never approximates, but is always precise enough that you can use it as a clock. If the moon's motion is proof that gravity is precise to a terrifying degree, then Earth's tides are the longest poem gravity writes every day, a poem you can see, touch, and even hear in the rhythmic crash of waves, like the heartbeat of the planet. And the most interesting thing is, tides don't happen once a day, but twice. Why? To answer, we must look at how gravity pulls the ocean. When the moon is overhead above a region of ocean, its gravity is slightly stronger than at Earth's center, pulling the water toward the moon and creating one tidal bulge. But surprisingly, the opposite side of Earth, completely away from the moon, also bulges upward, creating a second tidal bulge. This happens because the moon's gravity pulls harder on the near side and weaker on the far side, leaving the water on the far side behind, a little bulging outward. Earth rotates through these two bulges every day, producing two regular high and low tides. This is not easy to achieve. For the whole mechanism to work, gravity must obey the inverse square law exactly, must be stable, smooth, regular to the thousandth of acceleration. If gravity was slightly stronger or weaker, the tidal bulges would not be in the right place. If gravity missed a beat, even a little, tides would not align with astronomical positions. And if gravity were a random coincidence, imagine the oceans, one day one bulge, the next day 3, the next day none. The following day, water rising at midnight, then switching to morning. But in reality, tides are so precise that you can calculate high and low water years in advance. 18th century navigation depended entirely on this. When ships left London, New York, or Lisbon, sailors could open tide tables and know exactly when high tide would be in Manila or Rio de Janeiro. Civilization relied on the regularity of the tides. Now look at the numbers. Tidal force scales with 1 centured version of the inverse square. This means if the moon were 10% closer to Earth, tidal forces would increase more than 30%, a change large enough to disrupt many coastal ecosystems. If 10% farther, tides would weaken by more than 30%, and many shores would no longer be washed twice a day, altering biological cycles and ocean currents that nourish the seas. Meaning even a small change in gravity would turn this entire planet into a completely different place. And when we calculate tidal forces from both moon and sun, it becomes even more miraculous. Spring tides and neap tides occur in the lunar cycle, never missing a beat. No randomness could produce that perfect synchrony, lasting year after year, century after century. Did you know that when moon and sun align, the sea rises exactly as predicted by Kepler's tidal theory? And when they are at 90 degrees, the sea falls to its lowest, also exactly as predicted. Tidal forces do not work chaotically. They run smoothly like a perfectly lubricated mechanical machine. If gravity were random, this would not happen. Tides would be chaotic. The sea would never repeat itself, and life would struggle to emerge on coastlines, where tides regularly bring in nutrients and carry them away, creating cycles many biologists believe were the cradle of the first multicellular life. But tides are not chaotic. They follow a schedule you can write on a board and teach to children. They repeat on the 29.5-day lunar cycle like a gigantic natural clock, and that clock runs so precisely that it only drifts by about 1 minute every 13 months. Try letting a coincidence produce that level of accuracy. Impossible. Therefore, tides are not just rising and falling water. They are proof of gravity's absurd precision. They are the longest poem gravity writes on the surface of this planet, twice every day, never missing a beat. If tides are the poem gravity writes across the oceans, then the solar system is the grand symphony it has performed for 4.6 billion years. A symphony with dozens of instruments, planets, moons, asteroids, all keeping time in an eerily precise, enduring way, such that if gravity changed by even a tiny fraction of 1,000th, the entire score would shatter like a violin strung wrong. Look at the planets orbiting the sun. Every orbit is a perfect ellipse. Every planet has a stable period. Every motion obeys the inverse square law, Newton derived from Kepler's laws. But what is astonishing is not just that each individual orbit runs correctly, but that the whole system runs without chaos, without deviation, without collapse, despite millions of small perturbing forces acting continuously. If gravity were just a little stronger, planetary orbits would shrink and they would fall into the sun. If a little weaker, the whole solar system would fly apart and planets would escape their parent star. There is no large margin for error in existence. Yet for billions of years, the solar system has been stable to the point of near boredom, stable in the sense of perfection. Take Earth as an example. Average distance from Earth to Sun is about 149.6 million kilometers. If Earth were just 2% closer to the Sun, water could not exist as liquid. 2% farther, Earth would become a giant ice ball. Yet Earth's orbit varies only a tiny bit, eccentricity of just 0.0167, enough to create seasons, but not enough to destroy climate. This cannot be random. Moreover, Earth's orbital speed around the Sun is about 29.78 kilometers per s. If that speed changed by just 0.1%, comma, you would not be sitting here reading these lines. Not just Earth. Mercury, the planet most strongly perturbed by the Sun, still maintains a stable orbit, despite gradual bending and twisting. Over time, the precession cycle is accurate to the point that Newton's formula matches 99.99% comma. And the tiny remaining shortfall is exactly the window Einstein stepped through. Jupiter, the giant beast of the solar system, acts as a gravitational gatekeeper. Its mass of 1.9 quarters 10 kg pulls, pushes, balances millions of smaller bodies, and maintains inner solar system stability. If Jupiter were 10% more massive, many inner planets would not exist. 10% less, comets would rain relentlessly onto Earth. Everything is fine-tuned to an absurd degree. But the most beautiful thing is not just the stability of individual planets, but the rhythmic relationships between them. The things astronomers call resonances. If the solar system is an orchestra, resonances are how the instruments lock in with each other. The classic example is the Jupiter-Saturn pair. Their periods are nearly in 5:2 ratio, meaning 5 orbits of Jupiter correspond to roughly 2 of Saturn. Result, gravitational perturbations between them almost perfectly cancel out, creating long-term stability. Or Jupiter's trio of moons, Io, Europa, and Ganymede. They fall into a perfect 1-2-4 resonance. For every 4 orbits of Io, Europa completes 2, and Ganymede 1. Picture it. 3 marbles rolling on water, yet always keeping exact time. No strings, no manual adjustment, for billions of years. Could this be random? Certainly not. Or look at Neptune and Pluto. They fall into 3-2 resonance, meaning every time Pluto approaches Neptune's orbit, Neptune is not there. A tiny planet avoids collision with a much larger one for billions of years, simply because resonance keeps time like a dancer, avoiding their partner's steps. Randomness cannot repeat with that precision. Randomness cannot sustain that rhythm over a time scale longer than the entire history of life on Earth. But resonances do not just maintain stability. They are traces of a deeper order, a combination of mathematics, gravitational pull, and inertia interacting in ways where any small change in gravity would make the symphony disintegrate. Imagine what happens if gravity were 1% stronger. Jupiter would perturb Mars's orbit so violently it could not hold a stable path. Chaos would spread like fever. Mars disrupts Earth. Earth disrupts Venus. Venus disrupts Mercury. The solar system would become a shaking machine, each planet a gear knocking the next off track until everything collapses. Conversely, if gravity were 1% weaker, resonances would vanish. Jupiter could no longer shepherd millions of asteroids, leading to non-stop comet bombardment of Earth. No life could endure. And if gravity deviated by just 0.0001 in the exponent of the inverse square law, meaning instead of 1 layard it became 1 layard, vidas, tia, orbits would no longer close into ellipses. They would either spiral into the sun or fly open to infinity. No ellipses, no Keplers, no Newton, no planetary system, no life. When you see the entire solar system moving like an orchestra, each planet keeping exact time, exact eccentricity, exact period, exact resonance phase, you begin to see what I've been trying to show from the beginning. Coincidence cannot create a symphony. Coincidence cannot create billion-year stability. Coincidence cannot create perfect resonances between celestial bodies. Coincidence cannot create a structure so finely tuned that changing one part in 1,000 would stop the universe from working. But gravity does all of that. It is not random. It is not capricious. It is precise, stable, and beautiful. A beauty only mathematics can describe. And when you realize the solar system is not a lucky collection of planets keeping their distances, but an orchestra operating according to equations, you will understand why gravity cannot be coincidence. Gravity is structure. Gravity is order. Gravity is the rhythm the entire universe must follow, and this symphony has only just begun. The journey to uncover the power of gravity entered its most dramatic chapter in the early 19th century, when astronomers discovered that the orbit of Uranus, the seventh planet from the Sun, did not quite follow the path Newton's law predicted. The deviation was tiny, only a few arc seconds, but enough to make the sharpest minds of the time suspect was something wrong with the equation. Or worse, was Newton wrong? But before doubting a genius who had explained the entire sky for 2 centuries, 2 mathematicians, John Couch Adams in England and Urbain Le Verrier in France, proposed a bold hypothesis. Uranus's deviation was not because Newton was wrong, but because an unseen new planet was tugging on it. This was the moment science decided to test gravity with the biggest question: can an equation see a planet before human eyes do? Adams and Le Verrier worked independently, unaware of each other. Both used the same tool, pure mathematics. They assumed there was a planet beyond Uranus and began calculating its position, mass, and orbit based on the jerk Uranus exhibited. In other words, they let Newton speak through numbers. They did not measure with telescopes. They measured with equations. Le Verrier sent his results first to the Berlin Observatory in September 1846. His letter gave a coordinate in the sky and said bluntly, "Look here, there is a planet there." Galle and de Rest, the 2 Berlin observers, pointed the telescope on the night of September 23, 1846. Within an hour of scanning the sky, they saw a faint point of light, an object not in any star catalog. It moved exactly as Le Verrier predicted. That was Neptune, the first planet in human history, discovered not by sight, but by mathematics. This was not just an astronomical discovery. It was a resounding affirmation that Newton's gravity was precise enough to pull a planet into view from an extremely small deviation in another planet's orbit. Think about this slowly. Uranus is nearly 3 billion kilometers away. Neptune nearly 4.5 billion kilometers. 19th century mathematicians had no computers, no modeling software, no precise orbital data like today. Yet they still calculated the position of a completely unseen planet. If gravity were inconsistent, if it was strong one day and weak the next, if it changed whimsically, if the inverse square law were only approximately true, the whole calculation would have been useless. Neptune would not have been in the right place. It could not have been predicted mathematically. It could not have been found with a telescope. Gravity does not allow such arbitrariness. It seals every gap. It makes the entire solar system run like an exquisitely crafted machine, where even a 0.00001 degrees deviation in one planet's path is enough for Newton's equations to detect it. This was the most glorious triumph of the law of universal gravitation. A planet heavier than 10 circumflex, 26 kg, lying billions of km away, hidden behind feeble light, was discovered not by human eyes, but by a tiny deviation in Uranus's path that can only happen in a universe where gravity operates with absolute precision. Neptune is proof that Newton did not merely describe the universe. He predicted it. And here is the difference between science and coincidence. Coincidence cannot predict, but gravity can, down to the millimeter, the arc second, the orbit. When Le Verrier was told the planet had been found exactly where he calculated, he said a famous line, "I saw it with the eyes of my mind." That statement is not exaggeration. It is literally true. And it shows that the law of gravitation is not a crude guess, but a logical machine capable of illuminating parts of the universe the naked eye cannot reach. Neptune did not appear by luck. Neptune appeared because gravity whispered its position through tiny deviations in Uranus's orbit. And humans were subtle enough to hear it. If a law can lead you to a planet hidden in darkness, that law is not coincidence. It is order. It is structure. It is living proof that gravity cannot be a coincidence. The deviation in Uranus's orbit once led us to Neptune, but when we look at Mercury, the smallest planet and closest to the sun, the story becomes stranger. This time, Newton could not be saved. Mercury exhibits a phenomenon called precession of the perihelion. The point closest to the sun shifts slightly after each orbit. Newton predicted most of this shift, but there remained a shortfall of 43 arc-seconds per century, a number so small it is hard to believe. If you drew Mercury's orbit on paper, it would take tens of thousands of years to see this shift with the naked eye. But small does not mean unimportant. In physics, any repeating discrepancy is a whisper of a larger truth. Interestingly, 19th century scientists did not see this as Newton's failure. They simply thought there must be another planet, just like Neptune. They even named it in advance, Vulcan, a hypothetical planet closer to the sun than Mercury, small and faint enough to escape notice, but massive enough to pull Mercury by exactly the missing amount. Astronomers hunted Vulcan for decades. Some reported fleeting sightings, but no consistent evidence emerged. The story began to feel like a reminder. When a great model no longer explains reality, you do not throw the model away. You look deeper into its foundations. Newton was not wrong because gravity is capricious or random. Newton was wrong because he was right over such a vast domain that even the tiniest discrepancy became a sign of a deeper order waiting to be discovered. And then came a man who refused to patch the model by adding a phantom planet. Albert Einstein, with an idea so bold, no physicist of the time thought it reasonable. Gravity is not a force. Gravity is the shape of space-time. When Einstein published general relativity in 1915, he did not tweak Newton. He replaced the foundation. Instead of saying the sun pulls Mercury, Einstein said the sun warps the structure of space-time around it, and Mercury simply follows the shortest path in that curved space-time. This may sound philosophical, but its mathematics is extremely precise. Einstein plugged Mercury into his new equations and checked whether the predicted orbit matched observations. The result appeared like magic. Einstein's equations produced exactly the 43 arc-seconds per century that Newton missed. No more, no less. No rounding. No guesswork. Absolute precision. This was not a lucky patch. It was the sign of a powerful theory capable of explaining even the tiniest discrepancies nature allows us to see. Mercury became Einstein's touchstone, just as Uranus had been Newton's. The most important thing here is not that Mercury deviated, but the deeper content it reveals. When a physical law is truly correct, discrepancies do not destroy it. They guide the way to a greater truth. In a universe where gravity is random, Mercury would deviate differently every day. The error would be uneven, unpredictable. No model could fit, but reality is the opposite. Mercury's discrepancy is fixed, repeating precise, as though written in fine ink across the sky. A tiny planet orbiting a giant star, 50 million kilometers away, became the delicate needle to test which theory was strong enough to describe the universe. Newton led us to Neptune. Einstein led us to the nature of space-time. And Mercury stands as witness between those two eras, reminding us that nature is never random when it speaks through numbers. In science, when something doesn't fit, it is not a flaw, it is an invitation. Through Mercury, gravity told us don't stop. There is still a deeper layer, and precisely by listening to that invitation, physics entered the modern age, where space can curve, time can slow, and gravity is no longer merely a force, but the architecture of the entire universe. Mercury did not defeat Newton. Mercury gave Einstein the chance to complete the picture. And it is that absolute order, from Neptune's triumph to Mercury's subtle discrepancy, that shows gravity is never coincidence, but a unified system operating across every scale. Einstein stepped into the picture of gravity, not as someone shattering Newton's legacy, but as the first person to look through the beautiful paint to see the steel structure underneath the universe. If Newton said the sun pulls Earth with an invisible force, Einstein said there is no force at all, only space-time itself curving, and planets simply following the straightest path in a bent world. It sounds bizarre, but that very bizarre idea explains everything. I may retell it in the voice of someone obsessed with beauty and physics, would say this: gravity isn't what pulls you down, it's what makes the very ruler of the universe bend beneath your feet. This was the greatest intellectual leap in the history of science. Instead of treating space as a stage and time as a clock, Einstein fused them into a four-dimensional fabric. Space-time and gravity is simply the curvature of that fabric when matter is present. A star warps, space-time, and a planet moves like a marble rolling on that curved surface. And the fascinating thing is, the moment Einstein wrote his equation, one he described as beautiful to the point of pain, it immediately produced predictions Newton could never reach. Among them, the most spectacular was the bending of light. If gravity is curved space-time, then not only planets, but light itself must follow that curve. This wasn't a vague philosophical idea. It was a measurable prediction. Light from a distant star passing near the sun would be deflected by a small angle. Newton could have predicted this if he assumed light had mass, but his prediction was only half the value Einstein gave. This was the showdown between the two theories. If light bent exactly as Einstein said, gravity wasn't a force. It was the geometry of space-time. In 1919, a British astronomer led two expeditions, one to Principe Island in West Africa, one to Sobral in Brazil, to observe a total solar eclipse. They brought cameras, telescopes, and a bold belief that the sun's shadow would let them see stars right behind it and measure how much light had bent. The eclipse happened on May 29, 1919. The sky darkened, and the first photographs were taken. When the analyses were complete, the results shook the world. Light bent exactly as Einstein predicted. No more, no less. A victory not just in accuracy, but in essence. Einstein didn't just explain planetary motion. He turned gravity into a geometric property of reality itself. From that moment on, Newton remained great, but he was no longer the final word on gravity. Einstein became the new architect of the universe. What captivates me most about Einstein isn't the boldness of the idea, but the subtlety of the equation. If you're someone who loves structures that absolutely cannot be random, then Einstein's field equations are one of the most ferocious proofs. On one side, the curved shape of space-time, on the other, matter and energy. And the equation says, these two cannot be separated. Matter tells space-time how to curve. Space-time tells matter how to move. This isn't coincidence. This is a mathematical dialogue of absolute precision, the kind of unity so beautiful that people describe it as the only poem the universe signs its name to. Why? Because changing a single character in that equation would collapse the universe. No galaxies, no stars, no stable orbits, no us. And that's what Einstein understood deeply. The universe does not allow whimsy. Gravity doesn't work strong today and weak tomorrow. It doesn't curve randomly and then suddenly produce beautiful spiral galaxies like classical paintings. Gravity can only operate precisely if space-time has a structure consistent to an absolute degree. There is no room for randomness here. Look at another example. Time slows down in strong gravitational fields, something Einstein predicted and was later confirmed with atomic clocks at different altitudes. A clock near the ground runs slower than one on a mountaintop. This sounds absurd, but that's what space-time does. It makes time flow differently depending on curvature. For such a subtle effect to occur, gravity cannot be the product of coincidence. No chain of luck in nature could produce an effect that repeats with precision to parts per billion. And because Einstein's theory is so precise that any observational discrepancy becomes a sign of new phenomena, it became the most powerful tool in modern physics, predicting black holes, gravitational waves, and the expansion of the universe. All of it lies in the curving lines of space-time. What is miraculous here? One person with a blank sheet of paper and a pen wrote an equation that can explain the entire universe, from planetary motion, light bending around the sun, time flowing in valleys, to the merger of black holes billions of light years away. How can you believe that is random when one idea can describe hundreds of completely different phenomena with the same mathematical structure? We are no longer talking about coincidence. We are hearing the true voice of nature. Gravity is not an attractive force. Gravity is the geometric message space-time sends to every object. This is the shortest path you must take. Einstein didn't just correct Newton. He showed us that gravity is how the universe writes poetry, with curves, with rhythm, with beauty, so precise that no artist could recreate it. Once you understand that, you will never look at the night sky as a chaos of bright dots again. You will see a soft curved network holding, guiding, and organizing every motion from photons to planets through equations that cannot be coincidence. When Einstein completed the picture of gravity as the curvature of space-time, everything seemed to fit together beautifully until we looked at galaxies and discovered they were rotating too fast. Fast enough that, according to the gravity we know, they should fly apart like a wheel missing bolts. But instead of disintegrating, they maintain their graceful spiral shapes for billions of years. This cannot be random. If you take a galaxy like the Milky Way, with more than 100 billion stars, and measure the rotation speeds of stars at different distances, you would expect the rotation curve to drop off as you move farther from the center, just like planets in the solar system slow down farther from the sun. That's what Newton predicted. That's what Einstein predicted. But when astronomers observed in the 1970s, especially through Vera Rubin's work, they found the opposite. At the galaxy's edge, stars rotate as fast as or even faster than those near the center. This is the same kind of story as Uranus's orbital deviation. But this time it isn't one planet pulling another. Here, entire galaxies behave as though there is 5-6 times more mass than what we can see. An unwelcome but unavoidable conclusion: there is hidden mass in galaxies, a component that emits no light, absorbs no light, but produces gravity. We call it dark matter. The most important thing isn't the nature of dark matter, still unknown to this day, but what it reveals about gravity. Even without observable matter, gravity still operates with terrifying precision. If gravity were random, if it varied whimsically on large scales, every galaxy would have a different rotation curve, disorganized, impossible to describe with any unified model. But instead, every spiral galaxy we observe, from Andromeda to dwarf galaxies millions of light years away, follows the same anomalous rotation curve shape. Pay attention to this: billions upon billions of stars, spread across hundreds of thousands of light years, scattered through millions of galaxies, all behaving the same way. No randomness could produce such uniformity. This is gravity saying what you see isn't the whole story. But the equation is still correct. Indeed, If you add an invisible mass distributed throughout the galaxy, Einstein's gravity immediately predicts the exact rotation curve. No need to change the theory. No need for new forces. No need for luck. Just acknowledge there is something else with mass, but no light. The truth may sound suspicious. How can the universe be full of things we can't see? But if you're accustomed to gravity's precision, you understand that nature doesn't care whether we can see it. Gravity cares about one thing: mass, whether bright or dark. Another example, galaxies in large clusters, like the bullet cluster, move in patterns that only gravity can explain. And strikingly, the gravity comes from mass that doesn't coincide with where the hot gas shines, meaning the heaviest thing in the cluster isn't what we see. When light from more distant galaxies passes through these regions, it bends far more than the visible mass would allow, an effect called gravitational lensing. Once again, gravity isn't flustered. It simply follows the equation with such precision that it reveals something else must be curving space-time. Dark matter isn't a patch on the theory. It's a natural consequence of a theory so strong that the universe has no choice but to obey it. What always delights me is this: even though we don't know what dark matter is, new particles, new fields, or something stranger, gravity still operates perfectly like a piece of music, with all the notes present. We just haven't heard every instrument yet. And here is the key point. If gravity were coincidence, expanding the scale from the solar system to galaxies would show the model falling apart. But in reality, the model works exactly the same, simply requiring additional unobserved mass. This is just like when Kepler looked at Tycho's data. The law was already there, waiting for someone subtle enough to recognize it. Dark matter is a reminder that our understanding is incomplete, but gravity's consistency is unshaken, and it shows one truth: if a law remains correct, even when we expand observations to millions of light years, that law cannot be coincidence. It is foundation. It is structure. It is how the universe truly operates. After seeing galaxies rotate too fast, yet still obey gravity, you can't say it's just luck. You have to say something deeper is hiding, and gravity is pointing the way. When we move beyond a single galaxy and expand our view to galaxy clusters, superclusters, and then the entire cosmic web stretching tens of billions of light years, gravity no longer appears as a simple attractive force, but as a patient architect, quietly weaving the largest structure that has ever existed. What physicists discovered at these colossal scales wasn't the random chaos people once imagined, but the cosmic web, a network of filaments, great walls, dense nodes, and vast empty regions called voids, all linked into an incredibly regular map of matter in space. The first surveys in the 1980s, like the CFA Redshift survey, led by Margaret Geller and John Huchra, drew the first three-dimensional map of the nearby universe. What stunned everyone wasn't the distribution of individual galaxies, but how they formed gigantic walls, like the Great Wall, longer than 500 million light years. Later, stronger telescopes and deeper surveys revealed even larger structures: the Sloan Great Wall, and even the Hercules, Corona Borealis Great Wall, spanning billions of light years, structures so vast we have to call them superstructures at scales no one previously thought possible. But the strangest detail isn't the size, it's the repetition of the pattern. No matter which direction you look, whether surveying a region 100 million or 2 billion light years away, you see the same motif: chains of galaxies stretched into filaments, interspersed with vast voids, and at the intersections of filaments, massive galaxy clusters. This isn't a random but seemingly ordered distribution. It is a geometric network, consistent to an unbelievable degree, as though the universe was built from a blueprint. It is here that gravity reveals its true power, a law that doesn't just explain planetary motion, doesn't just arrange stars in galaxies, but organizes matter on scales of billions of light years. If gravity varied by even 0.001% in different regions of space, the cosmic web would never form. Galaxies would clump chaotically, clusters wouldn't remain stable for billions of years, and voids wouldn't be uniform. But what we observe is completely different. The cosmic web follows gravity's predictions almost perfectly, from small to large scales. This is verified by cosmological simulations. When researchers run simulations like the Millennium simulation, with tens of billions of particles representing dark matter and baryons, they don't program the shape of the cosmic web in advance. They only input the equations describing gravity and the initial conditions after the Big Bang. The rest, the filaments, clusters, voids, interwoven network, emerges automatically. No strange assumptions added, no model tweaks. Gravity creates it all by itself. And the strange thing is, those simulations match real astronomical maps to an almost unbelievable degree. This uniformity is further reinforced by gravitational lensing. Light from distant galaxies, bent as it passes through regions of high matter density. When astronomers map this light curvature, they see it red draws the cosmic web almost exactly. Stronger bending regions correspond to filaments or large clusters, weaker bending to voids. In other words, the universe's light is confessing that gravity is working exactly as the equations predict at every scale. That means gravity has operated steadily for 13.8 billion years, from tiny ripples in the early plasma, 380,000 years after the Big Bang, to the full structure of the universe today. And here is the key point. If gravity were 1% stronger, the universe would collapse into chaos, with no galaxies. If 1% weaker, matter would be too dilute to form stars or planets. But gravity sits exactly in that Goldilocks range, not by luck, not by chance, but because that is the deepest nature of space-time. Galaxy clusters, one of the largest structures in the universe, also bear the mark of this precision. A cluster like the Coma cluster contains more than 1,000 galaxies, yet their motions remain neatly contained in a single pattern. The gravity of the entire cluster, including dark matter, governs each galaxy's motion like clockwork. If gravity were random, even slightly, clusters would disintegrate in a few 100 million years, but they have existed for more than 10 billion years. That only happens when gravity isn't capricious, when it obeys a unified equation with no exceptions. And the most beautiful part of the cosmic web story is this: from the scale of the solar system to the scale of the entire universe, gravity operates by the same set of rules. No variation with position in space, no variation with time, no exceptions by direction of observation. If a physical law can organize hundreds of billions of galaxies into a gigantic network, maintain the stability of that structure for billions of years, and predict matter distribution precisely through bent light, then we are no longer talking about coincidence. We are witnessing one of the most fundamental orders of reality. Gravity continues to reveal an even deeper role when we look at the place where the universe's first light was born, inside stars. Every star you've ever seen, from the sun to giants like Betelgeuse or Rigel, exists because gravity performs one simple but miraculous act. It compresses gas, and when compressed enough, the gas heats up. When hot enough, fusion begins, and fusion produces light. It all starts with cold, diffuse hydrogen clouds, tens of light years wide. Without gravity, those clouds would drift forever, scattered in space. But gravity, with the patience of an ancient craftsman, pulls hydrogen molecules closer bit by bit. The initial pull is very slow, but as mass accumulates, gravity strengthens, accelerating the process exponentially. This self-reinforcing resonance, gravity amplifying itself, means even a tiny initial fluctuation in the gas cloud becomes the seed for a star. As the cloud collapses, temperature rises, first tens of Kelvin, then hundreds, then thousands of degrees. At the cloud's core, temperatures can reach 10 million degrees Celsius, and that is the magical threshold where hydrogen begins fusing into helium, releasing enormous energy. The instant fusion starts, a star is born. The light you see from the sun every morning is the product of this process, a near-perfect balance between two forces, gravity pulling inward and thermal pressure pushing outward. A star exists because these two forces balance almost absolutely. This is the point that always makes me laugh at nature's subtlety. If gravity were just 1% stronger, the entire star would collapse faster than fusion could result. Temperature skyrockets. Fusion races too fast, and the star burns through fuel in just a few million years. Not enough time for life to form on any planet. Conversely, if gravity were 1% weaker, the gas cloud would never compress enough for fusion to occur. No fusion, no light, no chemical energy, no carbon, oxygen, nitrogen, or heavier elements forged in stellar explosions. Such a universe would be cold, dark, lifeless, simply because stars never formed. Life, at least as we understand it, would be impossible. What fascinates me isn't just the delicacy of this boundary, but its repetition in every star, every galaxy, every region of the universe we observe. No randomness is subtle enough to produce a force strong enough to create stars, but not so strong as to destroy them. Another example, massive stars like blue giants operate in constant explosive states with rapid fusion, while tiny red dwarfs can live trillions of years. But whether large or small, all obey the same principle. Gravity compresses matter to the threshold where fusion can balance it. No exceptions, no random behavior. Even the birth and death of massive stars testify to this precision. When a heavy star compresses matter until its core reaches densities beyond electron support, what happens isn't chaos, but a regulated sequence. Core collapse, supernova heavy elements, ejected matter, redistributed new generation of stars. Without gravity, not only is there no light, there is no oxygen, iron, silicon, the very elements that make you. When physicists tweak the gravity parameter in cosmological simulations, even the smallest change destroys this chain. Increase the force, stars collapse too fast. Universe full of black holes. Decrease it, no stars, no heavy elements. But real gravity sits exactly between those extremes, in a corridor so narrow that if you compared it to a ruler spanning the universe, the allowed error is the thickness of a hair, a force just strong enough to enable fusion, but not so strong as to ruin it. I often joke that if gravity were random, no two stars would be alike, no two galaxies alike, no steady light, no fusion stable for millions or billions of years. But in reality, this universe chimes because gravity is a law that can be written as an equation, not a string of chance events. And precisely because gravity operates so uniformly, the light we see from a single star or from trillions in galaxies is a sign of stability. Light isn't a random flash. It is the inevitable consequence of a law so precise that any deviation would destroy life. When you look up at the night sky, what you're seeing isn't just light. You're seeing gravity writing poetry, compressing matter into hot points, then letting fusion turn those hot points into the universe's headlights. If gravity is strong enough to create stars, but also subtle enough to dictate the shape of the cosmic web, then Cavendish in 1797, 1798, inside his draft-proof room, proved something even stranger. Gravity is so weak at human scales that it's almost invisible. yet still completely measurable, and measurable with such consistency that it cannot be random. The Cavendish experiment sounds simple, but in reality, it is one of the most delicate measurements humans have ever performed. He suspended a light wooden rod from an extremely thin torsion wire, with two small lead spheres at each end of the rod. Then he placed two larger lead spheres nearby. If gravity were real, if Newton were correct, the large spheres should attract the small ones, twisting the rod by a very tiny angle, so tiny that the naked eye couldn't see it, so tiny that a breath of air would ruin the experiment, so tiny that Cavendish had to build the setup in a sealed room and observe it from outside through a telescope via the slit in the door. And what happened was miraculous. The rod really did twist, a tiny angle of about 0.16 degrees, but enough for Cavendish to say, "I have measured the gravitational force between two small objects." Pause and think about that for a moment. Gravity on Earth is what keeps you standing on the ground. Yet the gravity between two tiny lead spheres is so weak, it's almost negligible. And still it was measured precisely. A law described by a single equation that governs the orbits of planets hundreds of millions of kilometers away is the very same law that makes two lead spheres a few dozen centimeters apart, pulled toward each other by an unimaginable amount. That consistency is truly terrifying. And from that tiny measurement, Cavendish did something even more extraordinary. He calculated the mass of Earth, because from Newton's equation, we only know the product Gm, not G or M separately. By measuring G through the extremely small gravitational force between the spheres, he could deduce Earth's mass, its density, and how it compares to other objects in the universe. Cavendish found that Earth weighs about 6 times 10, circumflex 24 kg, an astonishingly accurate number for an experiment done with torsion wire, wood, and lead. Many physicists later described the Cavendish experiment as a magic-breaking moment. For the first time, humans didn't just observe gravity through planets or massive bodies. They directly measured it, felt it, quantified it at small scales, and the result matched perfectly with the gravity of the large universe. If gravity were accidental, if it worked like strong forces are precise, weak forces are sloppy, the Cavendish experiment would surely have failed. A force so weak it's almost zero would not repeat. It would not give consistent results. It would not be predictable. But Cavendish proved the opposite. Gravity is like a piece of music, whether played by a planetary orchestra or by two tiny lead spheres. It keeps the same melody, the same law, the same rhythm. Its absolute precision does not discriminate by scale. And that is what makes this experiment such powerful evidence against any idea that gravity is random. You cannot call a law accidental when it describes the motion of the largest galaxies, and at the same time explains the tiny twist of a thin wire in a sealed room. Cavendish measured something almost impossible to measure, but gravity, with its absolute consistency, appeared exactly as the equation predicted. In that moment, he didn't just weigh Earth. He weighed the impossibility of coincidence in the law of gravitation. No one can watch objects fall without feeling something strange happening in the universe. Everything from hammers, feathers, lead balls, basketballs, to your own body falls the same way. It's hard to believe, but it's true. And this isn't some cute trick of nature or amusing coincidence. It is a foundational power of the universe, a property so deep that Einstein's entire general theory of relativity was built upon it. That principle is called the equivalence principle. Its content is very simple. Gravitational mass and inertial mass are completely identical, or in plain terms, everything responds to gravity in exactly the same way. That's why in a vacuum, a hammer and a feather hit the ground at the same time, an idea spectacularly demonstrated on the moon in 1971 by astronaut David Scott. But the real beauty of this principle isn't in that impressive demonstration. It lies in what the principle forces us to conclude. Gravity does not discriminate. It doesn't favor heavier objects or dislike lighter ones. It doesn't change based on material shape or composition. No capricious force could behave with such perfection. A random force would always have weaknesses, strengths, anomalies, phase shifts. It could not make every object accelerate at the same rate, but gravity does, and it does so with precision measurable to 1 part in 10 trillion in the most modern experiments. And it is here that Einstein saw what no one before him had seen. The equivalence principle isn't just an interesting fact of nature. It is a window into the true nature of gravity. When he imagined himself in free fall inside an elevator, a thought flashed. If I'm falling, I feel no weight. I don't know gravity exists. Everything around me falls the same way, so I can't distinguish any force acting. I just feel myself floating. From that thought, Einstein reached a conclusion that changed physics forever. Free fall isn't a special motion. It is the most natural state when no forces act. And that is the moment gravity stopped existing as an attractive force. If in free fall you feel no force, then what creates the curved orbit of a planet? The answer thrust physics into a new era, curved space-time. We aren't pulled down. We are following the natural curve of space-time. And the reason everything falls the same is that objects don't respond to gravity. They simply follow the shape of space-time, and that shape makes no distinction between one object and another. What is astonishing is this: if the equivalence principle were wrong by even 0.001%, comma, Einstein's equations could not exist. General relativity rests entirely on the assumption that free-fall motion is identical for all objects, so that space-time can be described by a single geometric structure for all matter and energy. A universe where the equivalence principle fails would be a universe where no unified theory of gravity could be built. Moreover, every modern test, from the Uteverse experiment, sophisticated torsion balances, to the microscope satellite, confirms the equivalence principle holds within every measurable limit, no exceptions. No object falls a little differently. Everything hears the same instruction from space-time. This cannot be coincidence. A random phenomenon would not maintain precision at 1 part in 10 circumflex 14. It would not behave identically in every environment, from Earth to orbit, from the solar system to modern gravimetry experiments. It would not synchronize perfectly across billions of years of cosmic history. But the equivalence principle does all of that. When you drop an object, you are witnessing the purest signal of the universe. One of the deepest messages nature sends us: gravity is not a pulling force. Gravity is the shape of space-time, and all matter follows the path that shape lays out. No exceptions, no discrimination, no chance. This very absoluteness, the uniformity stretching from the ball, falling from your hand, to light bending around the sun, is the foundation on which Einstein wrote his field equations. And it is this very absoluteness that makes every idea of gravity as coincidence meaningless. The universe is not capricious. The universe is consistent to a terrifying degree. The equivalence principle is powerful evidence that gravity is not only correct, it is correct in a way that cannot be coincidence, correct from Cavendish's tiny laboratory to galactic scales, correct to the point that we can build an entire geometric theory of the universe upon it without a single slip. When watching objects fall or planets orbit, it's easy to forget that gravity is the weakest of the 4 fundamental forces, weaker to the point that if you place 2 electrons next to each other, the electric repulsion between them is stronger than their gravitational attraction. by 10 circumflex, 42 times. That's 1 followed by 42 zeros. One of the most absurd ratios nature has left for us. But the strange thing isn't that gravity is weak. The strange thing is that gravity is weak by exactly as much as electromagnetism is strong. And this ratio seems anything but arbitrary. If gravity were just a little stronger, atoms would not exist. Electrons would be pulled into protons before electric force could push them away. If electromagnetism were a little weaker, chemical bonds could not form. The material world, as we know it, would disintegrate at its roots. Yet this world exists precisely in an unimaginably narrow range, where the ratio between the two forces is 10 circumflex 42, not 10 circumflex 40, not 10 circumflex 45. The big question modern physics still hasn't answered is why that number. No theory explains this by chance. No one believes the universe rolled dice and luckily landed on exactly the ratio needed to allow stable matter, steady burning stars, enduring planetary orbits, and the development of life. When you change the 10 circumflex 42 ratio by just a few orders of magnitude, every familiar structure vanishes. Imagine gravity 10 circumflex 40 times stronger. Earth would collapse into a black hole instantly. Stars could not maintain balance. Everything would contract. Conversely, if electromagnetism were a little stronger, electrons would never achieve enough separation to form chemical bonds, and without bond, no molecule, no life. What fascinates me is that at any energy level, in any environment, at any scale, the 10 circumflex 42 ratio remains fixed, as though it were a foundational constant of the universe. You can smash particles in the LHC at terrifying energies. You can put 2 protons in billion-degree plasma inside a stellar core. You can measure electrons in a lab near absolute zero. The ratio between gravity and electromagnetism doesn't change. No random phenomenon could produce such stability, invariance, uniformity at this level. This isn't coincidence. This is a mathematical language the universe uses, and it is precisely because of that ratio that nature can operate the way it does. Gravity weak enough to allow matter to form, yet strong enough to gather matter into stars, planets, and galaxies. Electromagnetism strong enough to keep atoms stable, yet not so strong as to prevent large-scale matter from existing. These two forces are like two opposing musicians playing in perfect harmony. One, the deep, steady drum pulling everything together. The other, the sharp violin keeping particles in exact place. No current theory in particle physics or cosmology explains why this ratio is so precise. People call it the fine-tuning problem. But if you prefer a simpler, more direct name, you can call it cannot be coincidence. A universe in which two forces differ by 10 circumflex 42, yet combine perfectly to create structure, light, heat, atoms, molecules, and life, cannot be the result of dice rolls. Gravity is weak, but not arbitrary. Electromagnetism is strong, but not excessive. And the balance between them is the clear signature of order, not chaos. Gravity has proven its precision at every scale, from the electron level to the cosmic web spanning billions of light years. But when we try to bring gravity into the quantum world, where particles dance according to probabilities and vacuum fluctuations, suddenly everything becomes incomprehensible in a way no other force encounters. People often say gravity is very hard to quantize, but hard not in the sense of we're not smart enough yet, but hard in the sense that the nature of gravity was never made to fit the quantum framework from the start. This is something many physics students experience for the first time, when they see that the other three forces, electromagnetic weak, strong, all quantize smoothly, described by force-carrying particles like photons or gluons. But gravity, the most important force for cosmic structure, has no such simple force-carrying particle in the standard model. You can hypothesize a graviton, but when you try to build a quantum theory for it, the mathematics explodes. Infinities appear everywhere. The equations cannot be renormalized. And every attempt to plug gravity into the standard model ends in a pile of meaningless expressions. Many see this as failure, but if you look at gravity through the eyes of those who love nature's subtlety, you see something else. Gravity resists quantization because it is not the force in the way we think of forces. It is the geometry of space-time. Remember Einstein's general relativity. Gravity isn't a push-pull force. It is the curvature of space-time. This isn't a philosophical statement. It is a mathematical structure tested by hundreds of experiments. So how do you quantize something that isn't a force, but the foundational structure of reality itself? It's like trying to quantize the soccer field instead of the players. The other three forces are players on the field. Gravity is the field. From this perspective, gravity's resistance to the quantum framework isn't a sign of failure. It is a sign that gravity has a deeper nature than anything else, a nature the quantum model is not yet big enough to contain. And what's interesting is that every attempt to merge gravity with quantum leads to small windows, revealing its true essence. When you try to combine the two great theories, quantum mechanics and general relativity, you find you cannot do it without altering the very structure of space-time. String theory says space-time must have extra dimensions. Loop quantum gravity says space-time is made of discrete volume, quanta smaller than the Planck length. The holographic principle says space-time may emerge from information on a two-dimensional surface. These ideas sound fantastical, but they arise from rigorous mathematics, and all share one thing: gravity is not just a force in the universe. It is what creates the very architecture of the universe. Gravity's difficulty to quantize isn't because we're inadequate. It is a signal that gravity sits at the deepest layer of reality, where space, time, energy, and information merge. A beautiful example. When you try to calculate a black hole's entropy using both theories, general relativity and quantum, you get the famous Bekenstein-Hawking formula, which says entropy is proportional to the black hole's surface area, not its volume. This isn't normal matter behavior. This is the behavior of a geometric object, where information lives on the surface rather than inside the body. This only happens when gravity is not an ordinary force field, but a deeper structure, closer to information than to particles. Seen from here, the story becomes clearer. Gravity isn't hard to understand. Gravity is simply saying you're looking at it from the wrong angle. A capricious, random, or lucky force would be far easier to quantize because it would behave like the other forces. But gravity doesn't. It refuses to fit the quantum framework because its role isn't to exchange force between particles, but to decide what space-time shape those particles exist in. And that is the deepest nature of the universe we know. Before you ask, how does gravity act on particles, you must ask, where do particles exist when gravity itself creates that where? This cannot be coincidence. No random law could have a structure deep enough to determine the very shape of reality. Gravity resists quantization, not because it is messy. It resists quantization because it is too fundamental. It doesn't live in space-time. It is space-time. When we reach the deepest layer of the gravity story, we encounter a truth that makes even the most skeptical pause and think the universe only exists because gravity is fine-tuned to a precision that no randomness could ever produce. This fine-tuning isn't vague philosophy. It is cold, sharp, merciless numbers. If the gravitational constant g differed by just 1 part in 10 circumflex 60, the universe would have no stars, no galaxies, no heavy elements, and of course no life. What is 10 circumflex 60? It is a number larger than the total number of atoms in the solar system. To picture it, you shoot an arrow at a target the size of the entire Milky Way and hit a dust mote smaller than a proton. That is the level of fine-tuning at which gravity operates. If G were just a tiny bit stronger, not much, just 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000. Conversely, if G were weaker, by exactly that amount, fusion to occur, the universe would remain an eternal cold sea of hydrogen. No stars, no light, no carbon, no life. I want you to notice this. To create even one star, gravity must be strong, almost exactly to the decimal place. Because if weaker, fusion never starts. If stronger, fusion starts too fast, and the star dies young. There is no large margin for error. The universe never says A close enough. It demands exact, only exact, no deviation allowed. From that precision, everything you know was born. Carbon, the element that makes DNA, proteins, cells, and your very body, only forms in stellar cores through 3 extremely sensitive helium reactions that depend on the star's burning rate. If gravity was stronger, stars burn too fast. Carbon forms but gets burned into oxygen and neon before it can accumulate. If weaker, stars never reach temperatures high enough for carbon to appear. A tiny shift in G, a tiny shift in stellar burning rate, and the periodic table would be empty. No carbon, no organic chemistry, no complex life, no you reading this line. Everything you take for granted depends on gravity being exactly what it is, not allowed to differ by even 1 part in a trillion, trillion, trillion. Even more astonishing, when observing galaxy formation, if gravity was stronger by 1 part in 10 circumflex 60, galaxies would collapse into dense regions with no stable star formation. If weaker, galaxies would never condense. The universe would be an aimless sea of dust. No structure, no light, no time long enough for evolution. Many call this the fine-tuning problem. But that name doesn't go far enough. This is evidence, not in a philosophical sense, but in a mathematical one, that the universe did not randomly pick its gravitational constant. If gravity were random, the probability of it landing on exactly the one value in an infinite range that allows a livable universe is essentially 0. Some physicists calculate that probability is so small you need to write 60 zeros after the decimal before the first non-zero digit appears. This fine-tuning appears at every level: the initial curvature of the universe, the balance between matter and dark energy, the conditions preventing early hydrogen destruction, the quantum fluctuations in the Big Bang, neither too large, causing chaotic explosion, nor too small, leaving a flat, featureless universe. Every parameter sits in an extremely narrow window. Every parameter must be exact. And most remarkably, all these fine-tunings depend directly or indirectly on one thing: gravity. Gravity determines expansion rate. Gravity determines compression needed for star formation. Gravity determines galactic structure. Gravity determines stellar lifetimes. Gravity determines heavy element existence. Gravity determines whether a planet can retain an atmosphere. Gravity determines whether cosmic scale conditions remain stable long enough for life to evolve. You may have heard someone say, maybe this universe is just one of countless universes, and we're in the lucky one. But that isn't a scientific explanation. It's a way to dodge the most important question: why does gravity have exactly the value that allows the universe to exist? This cannot be chance. Even the multiverse hypothesis, if true, doesn't make the problem disappear. It only shifts the question to why does the underlying equation that generates the multiverse permit exactly this form of gravity? To date, no theory explains this fine-tuning by randomness. No model allows a slight change in G while still producing a structured universe. There are no neighboring universes in parameter space where life still exists. There is only one path, and gravity stands exactly on that path. When you look at the night sky, you aren't just seeing light from stars. You are seeing a law operating with such precision that if it deviated by 1 part in 10 circumflex 60, the sky would be empty. You would never exist to ask this question, and that very fact makes this the strongest argument we have. Gravity cannot be random. It is foundation. It is pillar. It is a law fine-tuned to the point that the entire universe must obey it. The universe did not pick randomly. Gravity did not pick randomly. It picked exactly, only once. And because of that, we have a universe to understand and a reason to stand in awe. So after all these layers of knowledge, these absurd numbers, this evidence stretching from the smallest particle to the structure of the cosmos, the final question still stands, staring straight at us like a challenge. What is gravity really? I don't know. That isn't humble modesty. It is the only honest answer science can give when facing something too vast to fit into a simple definition. But not knowing what it is in no way means not knowing how it works. The opposite is true. Of all the laws of nature we have ever discovered, gravity is perhaps the most consistent, the most precise, and the most beautiful. You may not know its origin, but you know it has structure. A structure that never breaks its promise. Gravity guides planets along perfect ellipses for billions of years. Gravity keeps the moon falling exactly 1/20th inch per second, as though rereading an ancient score. Gravity creates stars by compressing gas to precisely the fusion temperature threshold. Gravity sustains the cosmic web with an invisible hand so steady that filaments billions of light years long still hold their pattern. Gravity bends light exactly as Einstein's equations predict. Gravity makes 2 tiny spheres in the Cavendish experiment twist by exactly the predicted 0.16 degrees. No deviation, even by 1,000th of a part. None of those phenomena looks like nature's whimsical mood. They all look like structure, mathematical structure, geometric structure, informational structure. Gravity is not a joke, not random, not a lucky streak. It is enduring, repeating, measurable, predictable. So why can we describe gravity with equations so beautiful they sometimes make people shiver? Because nature is not as chaotic as humans thought before learning to ask the right questions. Nature isn't trying to make things hard for us. It simply sits there, steadfast, waiting for us to find the right key to the next door. Newton found one key, Einstein found another, and each time a door swings open, instead of randomness, we see only deeper layers of order. Remember this, every theory of gravity we have, Newton's, Einstein's, or the emerging quantum models, describes the same thing, just from different angles. Newton gave us force, Einstein gave us geometry. Quantum gravity may give us an even more foundational picture, where space and time are no longer the stage, but products of information. But whatever the final model is, one thing is already too clear. Gravity was not rolled out by dice to land on a random value. It is precise to the point that a deviation of 1 part in 10 circumflex 60 would mean nothing exists. It is consistent enough to lead us to an unseen planet. It is strong on cosmic scales, yet weak on atomic scales, by a ratio of 10 circumflex 42, a number no random theory can explain. It bends light, stretches time, births stars, builds galaxies, weaves the cosmic web, and ultimately creates the conditions for life to ask what is gravity. Instead of trying to box it into a definition, we should ask, why does nature allow us to see such beautiful patterns? Why does Einstein's equation look so elegant? Why does the inverse square law hold to the thousandth in hundreds of measurements? Why does the cosmic web match simulations so absolutely? If the universe were chaotic, why is there so much order? Because nature wants us to understand it. Or at least, it doesn't hide the important things from us. And we have understood a part sufficient to know that gravity is not a game of chance. It is a chapter in the book of the universe, a chapter we can read, translate into equations, and use to predict everything from a falling apple to galactic orbits. I don't know what gravity truly is at the deepest level, but I know something more important. It has structure. It is precise. It is not random. And every time we take another step, nature shows us another piece of the truth, as though smiling and saying, yes, keep going. The final answer is right ahead. After traveling the entire journey, from Tycho Brahe patiently measuring the sky with naked eyes, to Kepler solving 3 laws like poetry, to Newton gathering heaven and earth into a single equation, to Einstein turning gravity into the shape of space-time, then to dark matter, the cosmic web, star formation, the Cavendish experiment, the equivalence principle, the 10 circumflex 42 ratio between electromagnetism and gravity, and finally, the 1 in 10 circumflex 60 fine-tuning that decides the universe's existence. We return to the original question: is gravity a coincidence? After 21 parts, the answer shines clear without needing emphasis. No, not in an emotional sense, not in a philosophical sense, but in a mathematical, experimental, physical, and logical sense. Every piece of evidence we touch points to one single conclusion: gravity is not luck. Newton's law is accurate enough to discover an unseen planet. Einstein's equations are accurate enough to bend light to the arc-second. The cosmic web obeys gravity like a gigantic orchestra obeys its conductor. Stars burn correctly because gravity compresses matter to exactly the required fusion temperature. Life exists because gravity sits in an absurdly narrow range. 2 tiny spheres in the Cavendish experiment twist by exactly the predicted angle. Light is held at the event horizon, exactly as Einstein said. None of those phenomena looks like dice rolled and luckily landed right. They look like a mathematical blueprint that existed before the first galaxy formed. Even what we don't yet know, quantum gravity, carries no sign of caprice. It carries the sign of a structure so deep that every current theory must bow before its sophistication. That is not the image of a random universe. That is the image of a structured universe. A universe written in equations. A universe where every phenomenon, from photon to galaxy, fits together like the gears of an exquisite machine. Nature only shows us hints. The rest we must find ourselves. After these 21 parts, I can rephrase that more fittingly. For gravity, nature does not roll dice. Nature writes equations. If gravity were random, the universe would be toying with us. But I don't think the universe has that kind of sense of humor. It is too serious in the way it organizes stars, too subtle in the way it builds structure, too consistent in the way it keeps the moon falling exactly 2 mm per second. And as every good physicist knows, a beautiful law isn't beautiful because we like it. It is beautiful because nature allows us to see its truth. So the next time you look up at the night sky, remember that what holds billions upon billions of stars exactly in place is not a game of chance. It is an equation. And when you feel your feet pulled to the ground, remember you are not being randomly attracted to Earth. You are following a curve that space-time wrote long ago. This journey from the earliest observations to the deepest equations was never meant to prove we know everything about gravity, but to show that what we do know is already more than enough to conclude gravity is real, consistent, beautiful, and cannot be coincidence. The unknown part, that's where science keeps walking forward. The big questions about quantizing gravity, about the nature of space-time, about information and black hole entropy, all still wait. If you want to continue exploring with me the other secrets the universe is hiding in its equations. Please subscribe so you don't miss the next part. See you in the next adventure, where we open yet another door to reality.